I don't know if you ever got my email about the last quiz.
I think I did, yeah.
How the quiz didn't have any numbers on it.
Didn't have what?
Like how it said the list of the data.
Yeah, and it didn't have the values.
There was no data in there.
Yeah. So one thing that might have caused that is depending on what you opened the file with. So, like, if you open it through your email and you're using a particular browser, it might not show the values. The best way to open it is to use Word. Microsoft Word. So, what I was just doing is when you get that quiz, download it to whatever computer you're using, and then open it with Microsoft Word. You don't need to worry about that quiz though, because like I said in the previous lecture, I sent the wrong version out.
Oh, okay.
So the quiz Friday is going to be the one that matters, yeah.
Okay. I'm fine with that. Do that. I'm tired of all these documents.
I know that feeling.
Is there a lot of people on this class out, like COVID-wise?
In this particular class, I wouldn't be able to tell you, but overall through all my classes, there's a few, which is why I'm letting everybody, giving the link to everybody to the lecture, just in case they can't make it. Okay, well, looks like you are the only one right now. Oh, there's one more. You're Sparks, right? Jordan? Oh, I'm sorry. Jordan. Okay, 2 of us today. So let me just get the projector going for the distance learning guys, and then we'll be able to start. Which, those of you that are in the stream right now, I don't know why, but for some reason the program that lets you see the projector keeps crashing today. I don't know why. So if it crashes, just type here in the chat. Right there. And let me know. And of course, if you have any questions, type them into the chat as well. Alright, so let's go ahead and get started. So last time we were talking about standard deviations, and standard deviations are measurements that we can use to gauge, where data is in relation to the mean. So we have two different formulas for standard deviation. So for a population, if we collect data in a population, we say it's lowercase sigma equals the square root of the sum of all x values minus the mean, mu, squared, divided by n, the number of data points we have. And for a sample, it's very similar. We have s equals the square root of the sum of all data points minus the mean x bar squared divided by n minus 1. And again, we say that these give us a distance that we can follow, a distance away from the mean, to find where our data lies. And it's typically an amount of data. So how much data lies within one standard deviation of the mean? How much data lies within two standard deviations of the mean? So on and so forth. But again, the important part here is that standard deviations are a distance. So, can a distance be negative? So can I say that the distance from this wall to that wall is negative 10 feet? Does that make any kind of sense to say that we have negative 10 feet? No, distance can't be negative. We can't say that we can go negative 10 feet. It doesn't make any kind of sense. So when we're talking about standard deviation being a distance, it's the same thing. Standard deviation cannot be negative either. And that's worked into the formula itself. When we work these parts out inside of the parentheses, the x minus the mean, so x being any data point we have in our set. If this x is lower than the mean, so if it's less than the mean, it's obviously going to become negative. So maybe we do an x minus mean here and we get negative 2 for one of our data points. Well, once we get out of these parentheses, we have the square. So negative can, like I said, maybe in this case negative 2. Negative 2 squared is negative 2 times negative 2, and negative times a negative makes a positive. So no matter what, even if we do get negative values from our x minus mean, that square makes them positive. And then after that, there's nothing else in this formula that could possibly give us a negative. So standard deviations will always come out to be positive, and that's something you should remember when you're doing your calculations for them. If you get a negative number out for your standard deviation, something's wrong. You need to go back and look at what you did. So standard deviation is always positive. And again, it's a distance. It has to be positive. Sure. So this symbol right here, this is lowercase sigma. And this is just the symbol that we use to show standard deviation of a population. So if we gather our data as a population, this is what we want to show for our standard deviation. Now, a little bit confusing, this E-looking figure here is uppercase sigma. What uppercase sigma says is once you've done x minus mean, so you're going to take every single one of your data points and subtract the mean, and you'll get a new set of numbers. This means take all of those, square it, and then the uppercase sigma is add all of them together. So when you see an uppercase sigma, and I'll make it a little bit bigger so it's easier to read. When you see uppercase sigma like this, it means everything that comes after me, add it together. Take a sum. Mu is the way that we show a mean for a population. So similar to how we were saying, this lowercase sigma is the standard deviation for a population. Mu is the mean for a population. X bar is the mean for a sample. They're calculated the exact same way, but we need to make sure we know which one we're talking about. Are we talking about a population or are we talking about a sample? And then S is just standard deviation for a sample. So to learn more about this, there is the YouTube channel that all my lectures get loaded to, and you'll look for the one that is standard deviation. It's in a playlist called, Math 0342 Fall 2020? Yeah. And if you want, I can send you the link to that right now. Cool. So let me go to my channel real quick. Copy this link. And do you want it sent to your Soros or your iCloud?
The iPhone.
Okay. Alright, I just sent it to you. Alright. But again, standard deviation is a distance. Now, there are more types of distances that we can use to understand our data and how it's distributed as well. So again, standard deviation is a distance from the mean, just to see what that envelops. We have another way that we can split this up, which is into quarters. So we can split our data up into quarters. And this will give us what's called a 5-number summary. So let me show you what I mean. So let's say we have a set of data, 6, 13, 22, 5, 17, 18, 21, 2, 1, 4, 15, 2, 16, 14, and 3. First of all, if we want to know distances and relative locations of different points in our data, we're going to need to have these sorted out from least to greatest so that they're actually in some kind of relation to each other. So let's go ahead and sort this out from least to greatest. So we have 1, 2, 2, 3, 4, 5, 6, 13, 14, 15, 16, 17, 18, 21, and 22. Okay, so we've got our data sorted from least to greatest. Something important to remember is that with typical data, like this, we don't just have all the numbers from 1 to 22. We have numbers that repeat. We have numbers that are skipped over. Okay? So this is going to change how our data is arranged in relationship to each other. So what we can do is get this 5-number summary to get an idea of what this data looks like, spread out, and what the distances between each data point actually kind of look like. So here's how that works. First of all, a 5-number summary works by splitting the data up into 4 equal parts. So an easy way to do that is to think about it like this. If we wanted to split this ruler up into 4 equal parts, a good way to start is to split it in half. So then we can take each of these halves and split them into halves, and that will give us 4 equal parts. We'll have 1, 2, 3, 4 parts. We're going to do the same thing with our data. So again, first thing we want to do is split our data into half. So if we want to split into half, we need to know the halfway point. What is in the middle of our data? What number is the absolute middle? And so what do we call that absolute middle number in our data? What? Median, yeah. So we want to find our median here. So let's go ahead and count in and see where our median is, and we have a median of 13. So this is our median. That's the halfway point. Again, like I was saying with the ruler, once we have our data cut in half, we can split each half into another half, and so we'll get fourths that way. So just looking at this set of data here on this side, where's our median? 3. So that's another area. This is actually called the first quartile, or Q1. First quartile. Do the same thing on the other side. So what's the halfway point on this set of, this set of numbers? 17. This is called the third quartile, or Q3. So where's Q2? It's the median. Good. So again, this data is now split up into 4 parts. 1, 2, 3, 4. 4 equal parts. Okay? So what we can say about these points that we have now is that by the time we get to the first quartile, we have seen 25% of our data. When we get to the median, which is the halfway point, we've seen 50%. Again, 50 is half. Once we get to the third quartile, we've seen 75% of our data. 3/4 is 75 cents, right? Now, the other 2 numbers we need for our 5-number summary, are the minimum and maximum numbers. And that gives us the entire range of data now. If we only had the first quarter, second quarter, and third quarter, I'd be leaving out a lot of our data. So we want to have both ends of our data represented as well. Thank you. So again, if we include the minimum and the maximum, we have the entire range of our data. So for our 5-number summary, what we would say is our 5 numbers are just these that we've pointed out. So 1, 3, 13, 17, and 22. This is our 5-number summary. And these numbers are great, and we can use them for certain things that we want to calculate. However, if we want to understand this group of numbers a little bit better, what we'll do is we'll need a graph. Again, like I've said before in the past, humans don't understand numbers as well as they understand visuals. So we'll take this set of numbers and make them into a visual now. So what I'm going to do to make this graph is first make a number line. So, So I've made a number line that goes from 0 to 25. And the reason I've chosen to go from 0 to 25 is because it easily encompasses all of these numbers. Okay? So when you make a number line for yourself to make a graph like this, just make sure that all of your numbers will fit on the number line. And now, we just need to plot them. So 1 is right here, then 3 we have right here, then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is right here. 14, 15, 16, 17 is here. 18, 19, 20, 21, 22 is right here. And the way we want to now show our visual part of this is by boxing in the quartiles. So these three numbers here are first, second, and third quartile. So we'll draw a box around them. And then from those quartile ranges, we will extend whiskers to our minimum and maximum.
Can you do that again? For the boxes?
So the three numbers, the first, second, and third quartile, so these three numbers in the middle, will get boxes around them. This represents our quartile ranges. This is where we can expect to see a lot of our data. Then whiskers, or these little lines, come off of the boxes that go to the minimum and to the maximum. So now we can more easily understand how much distance is between each of these percents. Remember that when we got our numbers, these should be equal. I mean, we cut it up into 4 equal parts, right? But now that we're seeing it graphically, we understand they're not exactly equal distances to each other. So even though these are equal parts, they're not equal distances. So our data is distributed unevenly. And again, this graph that we've made, this box and whisker plot, allows us to understand a little bit more easily how much these things vary from each other. So like from our first quartile to our second quartile, or 25% to 50%, there's quite a bit of distance. Whereas from our 50% to our 75%, not as much distance. Which kind of makes sense. I mean, look at our first quartile. It's at 3, and then the next one's at 13. That's a pretty big jump. But from 13 to 17, it's not that big of a jump. And then these whiskers show us to the minimum and maximum, or basically our outliers. So how far do the minimum and maximum fall from our quartiles? Well, this one's not too terribly far, a little bit. This one's much further. So again, this is a graph that allows us to understand a little bit better what the distances of these quarters looks like. Again, these are perfectly evenly spaced quarters, but they're not evenly spaced when we get to a number line. Now, if this was 1 to 22 exactly, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so forth until we get to 22, each number represented, we're not skipping things like we do to 6 to 13, and we're not going to repeat things like these 2's here. Then, if we had something like that, this would be perfectly evenly spaced. We wouldn't have these weird differences in our spaces. But of course, that's not what data does. Data doesn't go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It goes, like in this case, 1, 2, 2, 3, 4, 5, 6, 13. It skips numbers and repeats numbers. So this is showing how our data is distributed. Any questions? Okay, Let's do another one for practice. So I've got a set of data here, 8, 7, 12, 12, 7, 13, 6, and 5. Okay? Again, what we want to know is the relative distances between these things. So if you want to know relative distance, relative position, first they need to be in some kind of order. So let's go ahead and put them in order. What's our first number? Keep going for me.
6, 8,
Perfect. 5, 6, 7, 7, 8, 12, 12, 13. Okay, so now that we've gotten an order, we want to split it up into 4 equal parts. So let's first split it in half. So split it in half again, we need to find our median. So where's our median for this? Let's look. Count in, yeah, we have 2. So what is our actual median here? And what's that? Well, think about it this way, 7 and 8. What's halfway between 7 and 8? 7.5. Yeah, 7.5. Okay, so there's our median. And like we did before, we want to find the median of each side now. So just this side of data, what's the middle of this side of data? The median. 6 and 7, so what's between 6 and 7? 6.5, yeah. Okay, how about this side? So what's between 12 and 12? 12, yeah. Okay, so we've got first number here. What is this number? It's the first quartile? Or if we want to just say something easy, Q1. What's this one? Second quartile, Q2. This one? Q3. Third quartile. All right. And what else do we need? Minimum and maximum. So there's our minimum, there's our maximum. So what is our 5-number summary in order?
5, 6.5, 7.5, 12, 13.
Perfect. There's our 5-number summary. And again, we can do stuff with those numbers. They're nice to know, but we want to be able to take a quick glance and see what the distribution of these numbers looks like graphically. So we're going to need to make a box and whisker plot. Again, let me make a number line for us. I'm going to go from 0 to 15 on this one. 1, 2, 3. Okay. So this again goes from 0 to 15. And now we need only to plot these numbers on there. So 1, 2, 3, 4, 5 is right here. Then 6.5 is in between 6 and 7. 7.5 is between 7 and 8. 9, 10, 11, 12 is right here. And then 13 is right there. Okay? So what gets the box around it? So which of the 5 numbers?
6.5, 7.5, 12.
Yeah. In other words, our quartiles. It's always going to be those quartile numbers that gets the box around them. Okay, now what do we need to add to this to make it final? Whiskers, yeah. So we need to extend whiskers from the edges of our box to the minimum and maximum. Okay. So the distance from our minimum to the first quartile and the distance from our third quartile to our maximum, these are really, really close to being the same, if not the same. However, when we look at our quartiles, we can see there's a big difference between the first to the second and the second to the third. So this one, again, is not evenly distributed. It's got some stuff going on that's making our graph a little bit lopsided. And that comes from having 2 7s, 2 12s, skipping the 9, 10, 11 there, Okay. Any questions? Making sense? Sounded good? Yeah. So, excuse me? So again, what we're trying to do with this is we're trying to split our data into 4 equal parts, okay? So to split something into 4 parts, you split it in half first, right? So if you had a pie and you wanted to split it into fourths, you'd first cut it in half, and then to get 4 parts, right now you have 2, you take each of those halves that you have now and split them in half, right?
So why do we need to make it into 4 parts?
It's to understand, basically humans are very good at understanding quarters, because money, things like that, we understand 4 parts. So if we can understand, okay, this is 25, this is 50, this is 75, this is 100, it's a little bit easier for us to comprehend. Also, having it split up like this makes some easier calculations on down the line. Okay? I mean, we could split it up into thirds, but it gets a little bit tricky there. We could also split it into 6 or 7ths or something like that. It just gets more complicated. Having it split into quarters is quite easy to do. But again, yeah, the way you do that is you first find your midpoint, so your median. And once you have that, you've split this data into 2 parts. Okay? So you can split this one into 2 parts to get 1, 2 parts. Split this one into 3, 4 parts. Any other questions? Yeah, you don't have to ask. All right. So what if quarters aren't really your thing? Well, we can go past the 5-number summary. We can go past quartiles and things like that. So let's say we have a set of data. 49, 59, 60, 67, 69, 72, 75, 81, 86, 88, and 93. Sure, we could find a 5-number summary for this, split into quarters, get our box and whisker. Okay, but what if we want some more specific percents? Okay, so maybe we want to find out where we reach 53% of our data. Okay? Well, how far would we have to go until we reach 53%? Well, just looking at it, I don't know. There's a very easy way to figure it out though. We just need two numbers. We need n and we need k. We've all seen n before. We actually know what it is. Yeah, number of data points. Perfect. N is just the number of data points we have. So how many do we have here? 11. So n's 11. K is actually already on this piece of paper also. It's the percent. However, remember, this has to be as a decimal. So move the decimal to the left twice. So don't use 53 in your calculation, use 0.53. So what we're doing here is we're saying, all right, 53%. We want to know where 53% happens in here. But 53% is out of 100. What we want to know is where out of 11, 53% happens. So that's why we need to convert this into a decimal. Now, to figure out where it happens in our data, we just take our number of data points and multiply it by the percent in the decimal form. So k times n will give us what's called an index. The index is the distance you have to go to get to this percent. So we just need to multiply. 11, see it that way, I guess. 11 times 0.53 is 5.83. So our index is 5.83. That's how many of these data points we have to go through before we get to 53%, is 5.83. Now, I don't want to have to count 0.83 steps. That's not going to be very useful to me. So instead, we're going to round this number. And we're going to round it to a whole number. So what would this be as a whole number? 6. So really our index is 6. So 1, 2, 3, 4, 5, 6 steps. This means that by the time we reach 72 in our data, we have seen 53% of the data. Now, if you want to be technical about it, it's really somewhere between 69 and 72 that we reach exactly 53%. Okay, but we don't care about those numbers in between because they're not in our data. We don't have, 71 in our data. It goes from 69 to 72. So we're going to ignore those numbers. That's why we're rounding to the nearest whole number. And so what we can say now is that all of these data points are in the lower 53% of our data. Maybe it is. Let's see, what is our mean here? Our median. 1, 2, 3, 4, 5. Yeah, that actually is our second quartile. Which second quartile, 50%. If we were judging this on a number line, so including all the numbers, it'd be exactly 50%. But since we're not including all the numbers, we can say, all right, by the time we've gotten to here, this is 53%. Does this make sense? Okay. So, y'all were probably relatively recently seniors in high school, right? Okay. And they gave you a ranking in your class when you graduated. So maybe they told you were in the top 10% of your class. So what they're doing there is they are taking GPAs, all the GPAs for all of the students in your graduating class. And imagine that these numbers are GPAs. Then they would say something like, okay, let's find the bottom 10%. Well, what they do is they plug 10% into this formula, figure out the index, and find where it happens in the data.
What do you have to look 10% at?
Do what?
What do you mean, what do you have to look 10%
10% would be what you use here. So our K would be 0.1. So let me go ahead and do this. So maybe we want to know where 20% is, the lower 20% of our class. So N would still be 11. We still have 11 data points, but our K would now be this as a decimal. So 0.20. So now we multiply 11 times 0.2, and we get 2.2. And if we round this to the nearest whole number, that means our index is 2. So we go 1, 2 spaces. Okay, so again, if we were imagining that these were the grade point averages for our students, this guy and this guy are in the lower 20% of the class. Okay? And so that's how they calculate those rankings for the classes. Does that make sense? What other questions do we have? Upper. That's a good question. So maybe they want to know the upper 20%. Well, obviously we can't use 20% for our number, can we? We've got to use, let's see, how would we get 20%? Well, if we can't use this, we've got to go the opposite direction. We know that all of this together would be 100%, right? So if we only want to know the upper 20%, we chop off that 20, 80%. So we use 80 for that percent. So N is still 11, K is now 0.8. We do 11 times 0.8, and we get 8.8. Okay, so that rounds to 9. So we need to go 9 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the 80%. Anything above it is the upper 20%. So these represent the upper 20%. Does that make sense? Good. All right. So that is about all the time we have for today. Remember, I'll be sending this lecture out in email, so if you want to go back over it anytime, you can. Okay. Friday, we got that quiz. So the stuff we just went over today and yesterday is going to be on that quiz, along with mean, median, mode, and weighted mean. All right, so I'll see y'all then.